Hello everyone, this is Tuhin Mujumdar, and today I'm going to talk about a fitting sparse Markov model to categorical time series using regularization. This is a part of my PhD thesis, which was supervised by my advisors Dr. Shomendra Lahiri and Dr. Donald Martin at NC State University. So I'll start with a brief introduction. What is an order 1 Markov chain, order 1 homogeneous Markov chain? So it's a sequence of random variables x1, x2, and so on over a state space mod sigma, over a state space sigma, so that probability that the random variable xt plus 1 taking some value at taking value small xt plus 1 given all the past states, all the past states depends only on the last state xt. Similarly, an mth order Markov model has the property that given all the past states, the evolution of the chain at a time point is dependent only on the previous m states. So now, higher order Markov models is useful in many real life scenarios like DNA sequencing, text classification, data compression, and many other. But there is a problem, added complexity with fitting mth order Markov model, is that we need to estimate the transition probability for all possible m tuples, that is sigma power m. And without any model specification or model reduction technique, the total number of free parameters that is mod sigma power m times mod sigma minus 1. For example, if mod sigma is 4, which is the usual scenario in modeling an AGTC sequence in DNA sequencing, and with m equal to 2, the number of parameters is 48. While with m equal to 3, that number increases to 192. And there are no intermediate models as well between those. So unless we have some model reduction technique, it will be difficult to reduce the number of parameters. In light of that, we introduce the notion of sparse Markov model. So what is that? So here we here the all possible mth order history sigma power n can be partitioned into k-naught many groups C1 through Ck0, so that any two m tuple that belong to the same group have the same transition probabilities. And this class of model is called sparse Markov model. And here the total number of free parameters is k-naught times mod sigma minus 1. So this allows us greater flexibility to model such higher order Markov model. And this generalization was first proposed by Garcia and Gonzalez Lopez, where it was named as minimal Markov models. Later, the Bayesian predictive methods and analyzing some sequencing data. In that context, the method was expanded by Jaskin et al. And Xiong et al. Now, our main objective in this work is to develop a data-driven method of fitting SMM, where we don't assume any number of groups or the transition probabilities. And we have some theoretical result that ensure the model selection consistency of our method. We have some simulation studies and the real life data application to classify genome sequences, which demonstrates that our model has greater applicability. Now I'll go to the methodology. Before that, I will have some notation. Like we denote the method of Markov model as x1 through xn, and we denote the set of all m tuple as sigma power m. The elements of that set is denoted by small sigma 1 through small sigma p. Here, of course, the p is mod sigma power m, which is the total number of m tuple. And for j equal to 1 to p, we have the transition probability. We have mod sigma dimensional transition probability vectors pi j hat, which is the empirical transition probability from the m tuple for the jth m tuple. Now, based on these empirical estimates, we try to divide them into different clusters through regularization. Now, here the objective function, which is basically a penalized criterion for some function rho, for some convex function rho, with respect to the variables b1 through bp, and the objective function is half times sum over pi j hat minus bj square plus lambda times wij rho of bi bj. So what happens? So if you look into the penalized criterion function, this equation, this treats the estimator pi j hat as correlated observation and penalizes the distance between all distinct pairs of the probability vectors. So if two vectors like pi j, say pi 1 hat and pi 2 hat, they are close to each other, then depending on the value of the tuning parameter lambda, we will have the solution that b1 equal to b2. So essentially, if two transitional probability vectors are close to each other, we are putting them in the, possibly we are putting them in the same group, and that completely depends on the lambda. And here throughout the lecture, we have rho of bi bj to be the L2 norm, the bi minus bj of L2 norm of the difference of bi minus bj, which is a suitable choice of penalization term. And so what happens here? So rho x basically the rho L2 norm, and we can view this penalized criterion function as a constant optimization problem. So that means we replace that bi minus bj to vl. L belongs to the L belongs to epsilon, and epsilon is the set of all distinct edges L1 comma L2. That means all set of all ij pairs, and subject to the condition that BL1 minus BL2 minus VL equal to 0. Now this variable splitting, the new splitting variable VL, that is being introduced to capture the difference between two group centroids. And this approach was first taken by G and Len, and there are many methods to solve this constant optimization problem, namely ADMM and AMA. So for both of them, we first set up an augmented Lagrangian, which incorporates the original penalized criterion plus the usual Lagrangian term plus a square error term with some tuning parameter nu. And this B, V, and gamma are the matrices of Bj, VL, and gamma L in their columns, respectively for j equal to 1 to p and L belong to epsilon. And for both the algorithms, B, V, and gamma are updated sequentially in each step. And for ADMM, if we start with the initial values B0, V0, and gamma 0, and small BJT, VLT, and gamma LT are the parameters after the T iteration, then BJT plus 1 is weighted average of Yj and pi bar hat. Pi bar hat is the average of all possible pi j hats. That means the 1 over p sum over pi j hat. And Yj is defined by this quantity. And we update VL at the the time point t plus at the iteration t plus 1 by this proximal mapping, and gamma L with this formula. So this is the usual ADMM update. And for AMA update, we update the BJT plus 1 similarly as ADMM, but we can put mu equal to 0, which simplifies to BJT plus 1 with this formula. And the advantage of AMA is, after some basic algebra, it can be proved that we only need to update B and gamma in every step. So we can skip updating V because there are some linear relationship among the variables. And the update for gamma L is given by the projection matrix over the set CL, where CL is defined by this state. And of this projection of CL, projection of this quantity to the set CL. Now, what are the differences that ADMM and AMA? That ADMM converges for any mu bigger than 0, but AMA converges for mu between 0 and 2 by p. For ADMM, for in general, that we require that a smooth part of the objective function to be only convex, but for AMA, it requires to be strongly convex. So here we have used the L2 square norm for the smooth part, so which is a strongly convex function. So we can apply AMA. And for ADMM, it updates all the variable, but for AMA, it's keep updating VL and tracks the gamma L for which only WL is the weights is bigger than 0. And AMA is much faster with sparse weight. That means when this weight WIJs, the WLs, so they are, if most of them are 0, then AMA is much faster. And so now the next question is, how do we select the tuning parameter lambda? The notion is, if lambda is small, the number of groups is higher. That means if lambda is 0, possibly so there will be p many groups. That means all transition probabilities are grouped into a singleton. Now, if lambda is increased, then possibly after so there's a thing that, so if lambda is increased, then the number of groups decreases, because some of the transition probability coalescing to form from the new groups. So now, how do we select the tuning parameters? So suppose for a given lambda, we have the resulting clusters C1 hat to K lambda hat, where K lambda is the number of groups for that given lambda. Now the common transition probability for those m tuples are estimated. That means for alpha equal to 1 to K lambda, we calculate the number of transitions from that set to a particular number of transitions from that set of m tuples to a particular state, divided by the total number of times the chain has hit that state. So similarly, we see the way we have computed the transition probabilities, empirical transition probabilities for each m tuple. So similarly, we have grouped them according to the resulting clusters. Now we take the log likelihood of that resulting states and the corresponding BIC score, and then we choose lambda by grid search. Now, since we have a model selection procedure here, so we need some theoretical justification. So before that, I would like to say something about some notations, and as I told that we have used rho as the L2 norm, and let the true partition of the state, which you of course don't know, and we try to estimate that to be C1 through Ck0, and the true transition probability for the state is R alpha, and P alpha is the cardinality of the group C alpha, and there are some algebraic quantities like WIB or mu ij alpha, and like pi bar alpha is the group mean of the estimated transition probabilities of the state C alpha. And importantly, there are two quantities, lambda minimum and lambda maximum. So this lambda minimum, this captures the maximum deviance between two elements in the same group, and lambda maximum, that captures some scaled version of the estimated group centroids, the minimum estimated group centroids with some scaled version. There are some quantity delta 1 and delta 2, which we will use in the later phase. Now we'll go to the theoretical result, the first one. So this says that for any lambda bigger than 0, the optimal solution, because we solve with respect to B1 through BP, the optimal solution Bj star lambda is a valid probability distribution. That means the elements of them are bigger than equal to 0, and the sum of them is 1. So this is done because we assume that B1 through BP, there has to be transition probabilities, but we don't incorporate this condition. But due to the novelty of the method of AMA, it's automatically guaranteed. That's been proved in this theorem, and we don't need to incorporate any new condition to establish those things. And the second theorem that says, under these two conditions, that Wij equal to Wji, which means the weights of the weights between two pairs ij, they are of course identical, and Wij is bigger than 0 for any ij in the same group. And the second condition is, if ij belongs to the same group, then the weight is bigger than some threshold. Then under this condition, we indeed have lambda minimum is less than lambda maximum, that probability goes to 1 with the tail going to 0 with exponentially as n goes to infinity. So we'll have the utility of this theorem later, because to ensure the model selection consistency, we need lambda minimum to be less than lambda maximum. But since they are random quantity here, we don't have that. We don't guarantee that it will happen. But as n goes to infinity, we can guarantee that this will happen. So this theorem ensures that. So theorem 3, this is basically a byproduct of the previous ones. And so this shows that with wij with a particular weight choice, like with the Gaussian, which is like exponential of minus phi of pi I hat minus pi j square, with the indicator that pi I hat belongs to the k nearest neighbor of pi j hat or vice versa, and k is bigger than some threshold and epsilon is less than some another threshold. Now under this above assumptions and this condition A1 and A2 are satisfied. So this shows that under some particular weight choice, this A1 and A2 condition that we have mentioned, these are indeed satisfied. And there's some corollary. The major corollary is if the model is balanced, that means if the true number of partitions, they are equal for all the groups, or I mean for the true partitions, the number of elements in each group are the same, then the perfect recovery is possible for any lambda between lambda minimum and infinity, which ensures that for a large amount of value of lambda, we can have perfect recovery. And then we have the last theorem, that if the conditions of the theorem 2 holds and lambda minimum is less than lambda maximum, then the BIC criterion, we choose the true model through the BIC criterion, that probability goes to 1 as n goes to infinity. And given that lambda minimum is less than lambda maximum, so basically what happens here, the conditional, the condition that lambda minimum is less than lambda maximum, that probability also goes to 1. And given that happens, we choose the true model through minimizing the BIC, that probability also goes to 1. Now we have some simulation study, and we numerically demonstrate the convex clustering methodology, and we'll focus mostly on the choice of Wij and compare them under those weight choices. And also we don't specify the number of clusters, so it's not feasible to compute the straightforward misclassification rate. Instead of that, we compute the measure the similarity between the true cluster and the obtained cluster through rand index and adjusted rand index. And we have it is shown that it's known that's a sparse, so it substantially improves the clustering quality. And hence we perform the clustering algorithm for each estimated transition probability vector by solving the convex of objective function, and for a appropriate regularization parameter lambda, which has been chosen by the BIC criterion. And we compute the Ri and ARI and repeat the experiment for 1,000 times for empirically estimating the average Ri and ARI and along with the standard error. And we also estimate the probability of perfect recovery. That means out of these 1,000 times, how many times we have the estimated cluster assignment is same as the true one. So here the setup is like this: mod sigma is 4, m equal to 3, and the true partition is that 64 triplets is divided into 4 group of size 18, 18, 15, and 13. And for alpha group, like there are, so basically there are 4 transition probabilities, and we can arrange them as a diagonal matrix of 0.7 in the diagonal and 0.1 in the off diagonal. And there are 3 weight choices. The first one is the usual one with exponential minus phi of pi I hat minus pi j square with the indicator function that pi I hat and pi j hat, they belong to the k nearest neighbor of each other. The second case is like instead of L2 square norm, we use the L infinity norm and the similar indicator function with L infinity distance. And then the third one is the L1 instead of L infinity is the L1 distance with the similar indicator function. And we take the chain lengths to be n equals to 1000 and 2000. Now, for n equals to 1000 to 2000, for the Gaussian kernel, that means the first weight choice, if you look into the ARI for n equals to 1000, this 0.81, and none of the time the true cluster have been recovered. For n equals to 2000, you can see that the probability of the true recovery is 0.14. But for L infinity distance, you can see that the ARI is 0.90 and 0.98. For even for n equals to 1000, the ARI is really higher, and the probability of true recovery also is higher. And for n equals to 2000, that of course increases to 0.664. For L1 distance, the performance is better than L2, but a little slight downgraded than the L infinity distance, especially in terms of the recording or for the recording the true clusters. So this shows that here the transition probability vectors are well separated from each other, and this suggests if the cluster centroids are well separated, the clustering performance get better and better with the L infinity distance, because in such scenarios, L infinity distance just I mean, if they're well separated, then the difference in the significant, if there is a significant difference in only one coordinates, then the weight involving the L infinity distance that gives the best possible result. So this is an improvement from the previous one, because these weight choices are new, and that has been not used in previous methods. So instead of using L2 square, we can use the L infinity here to get some better result. And now we go to the real data application part, and here is the proposed SMM methodology to classify the virus to the correct species, correct as a sample from the human being. And for each virus, there is a reference genome sequence is available, and which represents an ideal genome sequence from that particular virus. Now, the problem is when we collect genome sequences from human beings who are possibly affected with some disease. Now, if they're fully available, then we can match that with the possible reference sequences, and there are methods to identify the true virus. And there is no point of doing or fitting SMM in that case. But there are many cases where the full sequence is not available. For example, when you collect samples from human beings, they go through many mutations, or they mix up with some other diseases that leads to trimming of some part of the DNA sequences, or some parts are lost. So especially when we have a partial DNA sequence available, how we can identify the virus. So that's the major goal of our application. Now we collect all the samples and reference genome from the NCBI database, and genome sequence of 500 individuals are collected, and among them 200 are affected from SARS-CoV, 50 from MERS, and 100 from dengue, and 151 hepatitis B. And the samples are collected over different time periods, different locations. In particular, for COVID-19 disease, we try to incorporate different strains over different countries, over different time points, like when a strain is breaking out or something like that. And the lengths of the reference genome sequences are for the SARS, MERS, they are 29,000, 30,000, 10,000, and 3,500 respectively. Now what we do here, we first build a reference model from the reference sequence for each of the virus. Now for the ith virus, I got 1 to 4, the corresponding model is denoted by pi hat, because for each model we have a group clustering of the state spaces and the estimated transition probabilities as well. And so that for any test sequence x, like denoted by x1 to xn, pi hat x is the likelihood under the reference SMM. Now for any such sequence x, we classify it to the class argmax of pi hat x. Now for search and merge, we fit the SMM of order n equal to 4, and for the other two, we use n equal to 3. And from each sample, we randomly choose a contiguous segment of length 100 times epsilon % and compute the likelihood under the 4 models classified to the most likely class of virus. And we have taken sigma epsilon to be 0.05, 0.1, and 0.25. That means 5%, 10%, or 25% of the whole sequence is retained. Now, when epsilon is 0.05, the overall misclassification rate is 0.22%. Even with, so because SARS and MARS, they have higher dengue, they have a little bit higher, higher length of the DNA sequence, they perform better. But for hepatitis B, the total length is around 3,500. So when we take only 5% of the data of the sequence, that's like around 170 or 180. So that is not a very big number to get meaningful information. So that's why we expect that the misclassification rate is higher inside this hepatitis B. However, as we increase the segment epsilon value of the epsilon, this misclassification rate reduces to 15%, and with 25% of the data retained or the sequence retained, the misclassification rate is like 3.2%. This is really interesting because only with the 25% of the sequence, we can correctly identify the true virus with 97% accuracy. And like I said, that for lower sample or the lower length of the sequences, it's sometimes maybe not it's not giving very good result. But even with only 1/4 of the retaining 1/4 of the sequence available of a particular sequence available, we can correctly identify them with 97% accuracy, which is really good because our SMM method, because this is a Markov model, this utilizes the information from the reference genome in a compact manner and homogeneously through the sequence. So even with 1/4 of the data available, we can capture the diverse structure of the different parts of the different samples, and we can separate them out, separate any two different viruses. So that's the major utility of our method. And with that, I end my talk here. Thank you everyone for listening to it.